Okay, today we will consider basic perturbation theory. For two states. Now we have covered some of the basic ideas when I have considered the configuration mixing shell model, but I thought that it would be very good idea to cover up the details of this, and then again we will discuss the two level mixing problem in more details. So basically what we have initially is this. We have two states, say E1 and E2, and they are unperturbed, right? So there is an energy gap between them, delta E, and the wave functions being phi1 and phi2, right? And finally we want to know that as a result of the interaction what happens. So this is initially, and the final thing, it is question mark right now. We do not know. So what are the possibilities? The possibilities are that they can come close to each other or they can go far from each other. So there is this possibility or is this possibility, right? This one or this one. Good. We will consider more of this in detail. Now, before I proceed, let me tell you that here the total Hamiltonian, we can write it down as H is equal to E1, E2, and then there is interaction V, right? So basically phi 1 V phi 2, if this is equal to V, then this is also equal to phi 2 V phi 1. Okay, now let's start the game. Note that here we have basically H, total H is equal to H0, we can write, plus H prime. And what are this? This H0 is basically your E1, E2 having 0 diagonal elements, and this H prime is basically the interaction part, right? So non-diagonal terms will be there, right? The eigenvalues of unperturbed Hamiltonian H0, this is the unperturbed Hamiltonian, its eigenvalues, let me write it in a separate page. So unperturbed Hamiltonian is H0, right? Eigenvalues are basically E1 and E2. Similarly, it has the corresponding eigenfunctions are let me write it like this: A1, A2, and A2, B1, B2. Okay. Now note that H0 A1 is equal to E1 A1, right? So basically we have E1 into A1 is equal to, and to A2. Now this is satisfied. Now this is satisfied when A1 is arbitrary and A2 is equal to 0. So let us assume A1 is equal to 1. Then we have this A1 equal to 1, 0. Right. Similarly, we can have A2 equal to 0, 1. Okay. Now, using perturbation theory, let us consider the first order energy shift. So, first order energy shift. Right. Now for eigenvalue E1, we have delta E1 is equal to 1, 0 into 0 V 0, and here we have 1, 0 again. And what's the result is basically 1, 0 into, here we have the result is 0V. And what's the overall result? Overall result is 0. Okay, now let's find the same for eigenvalue E2. And this time we have del E2 equal to 0, 1, 0, 1, again 0 V 0, and this again 0, 1, right? And so this is basically 0, 1, V 0, and this is again equal to 0. So let us now move on and calculate the second order energy shift. Second order energy shift. Right? Okay. So let's start with the case for energy eigenvalue 1. Let me, before I proceed, okay, let me do this state. So this is, since first order, I will write like this, 1 over here. Okay. Now, okay, so this is for eigenvalue E1, and since this is second order, so let me write the 2 index over here, right? Okay, so this is equal to 0, 1 into 0 V 0. Remember, this is second order, so the ordering will be different compared to the first order. The modulus whole square divided by E1 minus E2, and if you do the calculation, what you will get is this following, equal to V square divided by E1 minus E2. Now let me write it in this way, minus V2, oh sorry, not V2, minus V square divided by E2 minus E1. Okay, fine. Now for the second case, second eigenvalue. The second order shift is equal to, right, okay, 1 0 0 V 0, and then again here we have 0 1 whole square, and again this time it is E2 minus E1, and if you do the calculation you will see that the result is just V square divided by E2 minus E1. Okay, now let us consider all of them together. Fine. So the total energies, therefore total energy using perturbation theory, but again here up to second order we have done, right? So the total energy, what's the value? So the total energy is lambda 1 equal to E1 plus delta E1 plus delta E2 shift, right? And this is equal to just, you see, E1 minus V square divided by E2 minus E1. Okay, now what is the value of lambda 2? Again this is equal to E2 plus, sorry, this should be 1. Okay, this should also be 1 here. This should also be 1, not 2. And this should be again 2. Okay, now this value is equal to E2 plus V square divided by E2 minus E1. Okay, basically what we have is the following. So initially if we have just the two states E1 and E2, you see, now finally what we have here is this. We have again two states whose energies are, the energy for this case is E2, this is basically lambda 2, right, or this one, okay, E2 plus V square divided by E2 minus E1, and this one is E1 minus V square divided by E2 minus E1. So what do you see the effect of perturbation theory is? So basically what we are seeing here is that each level here shifts by an amount, and that is an equal amount, and in the opposite direction. So as a result of perturbation theory, the two levels, you see, they repel each other. Okay, this is the first observation, and the second observation is that one of the states with lower energy, this one, this has become more bound, and the state with the higher energy, it has become less bound. You see, more bound means going in deeper in energy, right? So let's write it down, these observations. So observations. Again, this case here that we have shown, it is important to say that initially we have E2 greater than E1. Okay. So observations. Right? Number 1, each level shifts by an equal amount. And what is the amount? The equal amount is V square divided by E2 minus E1, right? It shifts by an equal amount, okay, but in opposite direction. So this means that, so we can say that as a result of interaction or perturbation, you can say, perturbation, what we are seeing is that the two levels repel each other. Okay, so this is important observation. Two levels repel each other. Fine. And the next one is that one of the states with lower energy becomes more bound, and the state with higher energy it becomes less bound. Okay, so this is the next observation. So one of the states becomes more bound, and the state with high energy, it becomes less bound. See, so these are very important observations. Now you see, it is also important to note that here you see the shifting, basically it also depends. So this is also an important observation. Number 3, the shifting of the energy levels, it depends on number 1, magnitude of, let me write it correctly, magnitude of off-diagonal matrix element. That is V. Okay, or let me write it more correctly, off-diagonal matrix element of H, and that is basically V. So greater the value of V, greater is the Greater the value of V, just a second, greater is the relative shift. Why? Because you see, the shifting is basically depends on, here I have just showed you, V square by E2 minus E1. So V we are talking about, right? Now the second one is, so basically the shifting depends on V. This is what I am saying. And the number 2 is that it depends on the interaction of the levels. The levels E1 and E2, right? And also the level difference. This is also important. So it is also proportional to, you see, E2 minus E1. Now you see that as a result of this perturbation H prime, the energy of the levels change, right? And so the levels basically shift, this as we have seen over here. Now the effect of the perturbation is to make the interaction between the two levels weaker. So you see not this one, the effect of perturbation is to make the interaction of levels weaker. Why? Because you see, as a result of the interaction, the levels are being separated, right? And you see, if E1 and E2 are more closely spaced, then this difference will be less, and here you see the entire thing depends on denominator. So if the levels are more closer to each other, then this will be large, right? So if E1 and E2 are closely spaced, then shift is large. Now it is important to note that we can get the same result even if we use diagonalization instead of using perturbation theory. But of course, diagonalization is a much better method, right? Also, let us consider a different case. So where a different case, let us consider this, where initially the system is in one of the eigenstates. So initially system is in one of the eigenstates, E1 or E2. Now, so we will write H0 equal to E1 0 0 E2, right? Now suppose that our system interact with the surrounding and it feels as a result of this interaction a perturbed Hamiltonian, and that perturbed Hamiltonian is little bit different from the previous case. So suppose the perturbed Hamiltonian is this, right? So that now the total Hamiltonian equal to H0 plus H prime, it becomes basically, you see, E1 plus A 0, no, not 0, it will be V, and here it will be again V, and this one will be E2 plus B, right? Now how will you do the calculations? Now it's again quite straightforward, and let me just give you the result which you can straightforwardly get by diagonalization. So let me show you the result. The result is that in this case we will get lambda 1 is equal to just a second. Yeah, in this case we will get lambda 1 equal to E1 plus A, right, minus V square by delta, and lambda 2 we will get again E2 plus B. Let me write this, E2 plus B, and this time plus V square by delta. So you see the same thing is happening. And what's the value of delta? The value of delta is again little bit different. So it is basically the difference between the two. So the value of delta is E2 plus B minus E1 minus A. Okay. Okay. So you see this is what we have. Now let me write it down. Let me draw the picture. So we are considering the case where E2 is greater than E1, right? Yes. So let's again start. So basically we will have here E1 and E2, which we have initially, right? So this was E2, this was E1. Now suppose as a result of interaction, the system, we have a new set, right? And so what's the value? The value here is basically E2 plus B, and here we have again E1 plus A. And as a result of interaction, what we were having now is this. And what is the value? The value is, you see, E2 plus B plus V square by delta. And here we have E1 plus A minus V square by delta. See? So this is what we have. And this is when A and B are both positive, right? And this is finally what we get as a result of the interaction. So you can say that the diagonal elements A and B of H prime matrix, right, it basically shifts the E1 and E2, and then the off diagonal elements, right, basically V, it further shifts E1 and E2, and we get this overall picture. So this is initially and this is finally. Okay, so this is the scenario. Now you see, sometimes it is important to compare these two. That means the effect of the off diagonal matrix element with that of the unperturbed energy. So you see, this E1 and E2 is basically your unperturbed energy, right? And sometimes we try to compare them. So now let us try to compare V and E2 minus E1. Now what I am going to do is basically I am going to talk using diagonalization. So this will also give you a flavor of this, right? So diagonalization for two states. Let us do that. So basically we have the Hamiltonian E1 V E2. We will consider the simple case, not the plus A plus B case. And as again we are assuming E2 is greater than E1, right? Okay. Now for non-trivial solution, so for non-trivial solution we have E1 minus lambda, and here it is V. It is again V, and here it is E2 minus lambda, right, equal to 0. And so this gives us basically lambda is equal to half of E1 plus E2 plus minus half of again E2 minus E1 square plus 4 of V square, right? Now it is quite straightforward to see that this gives us the again the eigenvalues. But now we are not interested in that. We know that we get it from there. So again lambda plus minus to two values. Now what we want to do is compare these two. So how do you do that? So let us define a ratio. Let us define a ratio R, which is defined as delta E unperturbed divided by your interaction matrix V. So basically this is E2 minus E1 divided by V. So let us do the definition, right? Now you see, if we do that, then instead of lambda plus minus, let me write the two values E1 and E2 like this. So we have two values E1 and E2, and we can write it like this: half of E1 plus E2 and plus minus we have delta E unperturbed, that means this value E2 minus E1 divided by 2 and multiplied by 1 plus 4 V square divided by again delta E unperturbed whole square, right? Now you see, so basically we can write this expression again, rewrite it as this value, this form. You see, this we can write as half of E1 plus E2 plus minus half of delta E unperturbed into square root of 1 plus 4 by r square. Thus you see, the difference between this E1 and E2 can be predicted from the value of r. Between this E1, E2 and E1 can be predicted from value of r. Okay, now let us consider this case. Say delta E unperturbed, this is not equal to 0, that means non-degenerate case. Then again, number 1, if V is large, if V large, then what? Then R tends to 0 and E2 minus E1, this gap, this difference, this is basically large. Now, next case, if V is small, then what? Then basically R tends to infinity and here E2 minus E1 is small. See how easy it becomes. Now you see again the new, suppose let the old wave functions be phi 1 and phi 2 and the new wave functions, let them be psi 1. So what is the value of psi 1? Psi 1 is, we can write as a linear combination. So let me write it in this way. And psi 2 is equal to minus beta phi 1 plus alpha phi 2. Psi 1, psi 2 as a function of this. So this is old and these ones are new. Okay, now you see it is interesting, and you can also check this, that basically by diagonalization of 2 by 2 matrices we can get this result, and that is beta is equal to 1 divided by, again, 1 plus R by 2 plus square root of 1 plus R square divided by 4. Okay, and this whole thing whole square and this to the power half. So this we can get. Now you see, if your delta E unsuppressed here, if we have considered this case, right? So we have considered this case when delta E unsuppressed is not equal to 0. And what if it equals to 0? Then we have initial states are degenerate. So just a second, yes, here. So basically for delta E right. So we have just considered when this unperturbed delta E is not equal to 0. Now let us consider what if this is equal to 0. Then this means initial states are degenerate, right? And you can see that this gives us basically R tending to 0. Now this is, you get this even if V is small or large. You will get this R tending to 0. And then you will see in this case this beta becomes equal to 1 by root 2 and this becomes equal to alpha. So what does this mean? This means that there is, so this implies there is 50% or equal mixing between two states, right? And this is, in fact, this is the maximum possible mixing. So we have successfully considered both the unperturbed case not equal to 0 and this case as well. And you see the importance of considering the energy eigenvalues. So we have successfully obtained this result, right? Now, before I finish today's lecture, let me just talk about something. And what's that? So you see, we have seen that our results, they give us, because of the perturbation, we get this thing, right? And we do not get this thing. So this we do not get, and this we get. So this is what we get, but this we do not get. And the question is why? Why is it so? You can ask yourself, right? So why is this not possible? Now you see, let's look into the result. It is very natural, and you will see for yourself. You see, the ground state of a system is always the most stable configuration, right? Ground state is the most stable configuration. There is no doubt about it. And so it must lie deep below in energy diagram. Now, as a result of the interaction between the two levels, 1 and 2, if the ground state becomes less bound, like here, so here the ground state becomes less bound, then what does this mean? So here ground state becomes less bound than before. So what does this mean? This means that somehow due to interaction, the potential energy doesn't become minimum. So this means due to interaction, the potential energy doesn't become minimum. Right? Now this is not possible for a system in equilibrium. And so this is just not possible energetically. Right? So this is impossible for system in equilibrium. And so this is the reason why this is so. Okay, this is the reason for getting this result as the one. Okay, so with this I'll conclude this lecture today. If you have any questions, do ask me.